Kinetic molecular theory. This is the simplest model for the behavior of gases, and it explains a lot of things. So here we have a picture of a flask with gas particles. And so kinetic molecular theory looks at a gas as these individual particles. The particles are moving. They're moving in straight lines until they run into something, and then they bounce off. And those collisions are elastic collisions. So if you've taken physics, you might know what that is. Elastic collision is two things bump into each other, and the total kinetic energy after the collision is the same as before. You can have, this is, with real-sized objects, we don't have truly elastic collisions in real life, but billiard balls approximate them. So with billiard balls, if you roll two balls at each other and they collide, they're going to bounce off and they're both moving. And the total speed is about the same as what it was before. You can also take a ball and roll it at a ball that's standing still, and then afterwards the ball that was still is now moving fast, and the other ball might be just moving slowly, but the total kinetic energy is the same. So that's what happens with these gas collisions. So when they run into something, they don't lose any energy. So they are literally bouncing off the walls of the container, and they will just continue to do that, and they're never going to slow down. Because there's no friction, there's no wind resistance, there's no air resistance, because it is the air. So these particles are literally moving through nothing. They're moving through empty space, so there's nothing to obstruct them. And when they bounce off the wall, they don't lose energy. You guys still know what the game Pong was? So the original video game, right? So boring now. Get this little paddle. It was super cool at the time. Little paddle, yeah, little blip, right? And so you move the paddle at the bottom. It's just this line. Move the line at the bottom, and this blip goes around. And you have to catch it, and it bounces off. And it never slows down. And sometimes you could get it stuck, so it would just bounce all by itself, and then you could go off and eat a sandwich and come back, and you've got like so many points or something. Yes?
We finally upgraded onto that one. There's go against each other, you have a little castle. You bounce the ball into it. It's what we do with the Atari.
Yeah. Yeah, you guys missed out. There's just so many great things. Anyway, yeah. So this is like Pong, okay? So gas molecules are like that Pong blip, and they just bounce around, okay? So let's look at the different parts of kinetic molecular theory. So the size of a particle is negligibly small. Gas particles do have volume, but here it's so small in comparison to the total volume of the gas that it doesn't matter. They do have mass, okay? So gases are like Wyoming, right? The big state, so few people, it doesn't matter how big the people are. As opposed to people on an elevator where the size of the people matters a great deal, right? Lots of empty space. So just example, at STP, argon atoms occupy only 0.01% of the volume of the gas. So if the argon atom was the size of a golf ball, its nearest neighbor would be 4 feet away. So golf ball, 4 feet, next golf ball. Mostly empty space. So the size of the golf ball doesn't matter. The average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. So temperature is a measure of average kinetic energy. And we talked about that and how a solid, as it warms up, the particles are just like wiggling in their chairs, right? And not moving relative to each other, but just wiggling around. Well, in a gas, the particles are actually moving. So you heat up a gas, and the gas particles are moving faster. It's important to understand that it's the average kinetic energy. So some of the gas particles are moving really fast, some of them are moving really slow, a lot of them are in between, but the average is proportional to the temperature. Third thing is the collisions are elastic. So when the particles collide, they can exchange energy, but there's no loss of energy. And so that's why they just keep moving. There's no need for input of energy or anything. So here we see two billiard balls. Well, they're coming this way. They crash into each other and they bounce off. There's no loss of kinetic energy. Whereas if you do that with lumps of clay, if they were that lumpy, they probably wouldn't roll at all, but you get the idea. You roll those together and they're just going to flunk and they're going to stop. Now, did energy disappear? Was it destroyed? No, but it was transformed into heat. When those things hit, there's going to be an increase in heat. Maybe not anything you could detect with your hands, but that's where the kinetic energy goes. But that doesn't happen for gases or particles. Okay, so kinetic molecular theory explains all these things that we've been talking about in this chapter. So gas pressure. Gas particles are constantly moving. They strike the sides of the container with force, right? And so the pressure is force divided by area. Pressure equals force divided by area. So these particles are very small, and so the force that they hit with is very small, but there's so many of them that it is significant. So the result of that is pressure. I kind of forgot what I was going to say. Boyles Law. That was PV equals PV, P1, V1. The volume of a gas is inversely proportional to the pressure. So if we decrease the volume, we're squishing the molecules into a smaller space. Is there a picture? No, there's no picture. So we've got the same number of molecules in a smaller space. Their average kinetic energy is the same because it's the same temperature. And so they're going to run into the container walls more frequently, right? So that's going to cause an increase in the pressure. So you make the volume smaller, the pressure increases. Charles' law, volume is directly proportional to the absolute temperature. So if we increase the temperature of a gas, the average speed increases because the average kinetic energy increases. So increasing the temperature is going to cause the particles to move faster, so they'll hit with more force, and they're going to hit more frequently. So that would increase the pressure. But in a Charles' law problem, we're keeping the pressure the same. And so in order to keep the pressure the same, we have to allow the gas to expand. So the volume gets bigger when the temperature goes up. Avogadro's law, the volume of a gas is directly proportional to the number of gas molecules. Again, if we add more gas molecules to a sample, now we have more molecules in that same volume. They're going to hit more frequently. To keep the pressure constant, we have to allow the volume to expand. Dalton's law, total pressure is the sum of the partial pressures. So particles have negligible size and they don't interact with each other. When they bounce off, they just bounce off and they don't make relationships or anything. Particles of different masses are going to have the same average kinetic energy. So because the average kinetic energy is the same, then the total pressure of the collisions is the same, and it doesn't matter what the gas is. You can have different sizes of gas molecules. They're going to be going at different speeds, but their average kinetic energy is the same, and so their pressures are the same, so we can just add them up like they were the same thing. The ideal gas law. So you can derive PV equals nRT from the principles in kinetic molecular theory. And the book has a nice derivation, and And I'm not going to do it in class because it takes a lot of time, and I think most of you don't care. And you don't need to know that, so just look in the book if you want to see how that works. But the theory predicts gas behavior that is consistent with observations and measurements. This model breaks down under certain conditions, but if we study those conditions where it breaks down, we can actually learn even more about gases. So we've been talking about temperature and velocity. So the average kinetic energy of gas molecules depends on the mass and the velocity. So this is the general equation for kinetic energy. 1/2 the mass times the velocity squared. Velocity is speed. So if gas particles have different masses, the only way that they can have the same kinetic energy is if they have different velocities. So a small particle is going to be moving faster, and a large particle is going to be moving slower. And, my boys are in football, and it's football season, and so I think of football players colliding with each other, right? And the small guys on the football team are usually really fast, right? And so when they come and tackle you, they're moving really fast, and so they can probably knock you down. But then you got the guys on the line, and they're big, but they can't move as fast. But because they're bigger, they can knock you down without moving as fast, right? So big guy moving slow can have the same amount of kinetic energy as a small guy moving fast, right? So in a gas mixture, the lighter particles are going to be traveling faster than the heavier ones, just like football players. So we talk about average kinetic energy and average velocity. The velocity we're using here is called the root mean square velocity, and the symbol for that is URMS, root mean square. It's a special type of average that we're not going to worry about what exactly it is. It's real similar to the average velocity. So the root mean square velocity of a collection of gas particles is going to be related to the temperature and the mass of the particles. The temperature tells us about the kinetic energy, and the mass and the velocity then are related. And so we're not going to worry about where this equation came from, but bang, there it is. And I'll give this to you on an exam as well. This is what I'll give you. The equation and R. Now this R looks different than the other R we've been using. It's the same quantity in different units. So this is joules per mole Kelvin instead of liter atmospheres per mole Kelvin. And then the other thing we need to watch out for here is in this equation, the molar mass needs to be in kilograms per mole. And we'll see in an example why that is. If we look at the distribution of velocities for different sized gas particles, here we have relative number of molecules with that velocity versus the velocity. So here for oxygen, we see that we kind of have this bell curve. It's a little distorted out on the high end, but it's a pretty nice bell curve there. And so we have this distribution. This is the most common velocity for the oxygen molecules at this temperature. And then as you go higher, there's fewer and fewer. And as you go lower, there's fewer and fewer. So we know that at a higher temperature, the average kinetic energy is higher, and so the velocity would have to be higher. Or if we're looking at the same temperature, if the mass of the particle is larger, the velocity is slower, or if the mass is smaller, the velocity is larger. So we might expect that we could just take this red bell curve and move it out for the smaller gases. But what we see is we still see a curve, but it broadens out. So there's a much wider range of velocities. And that piece of knowledge there is very important in little tiny bits of science. So most people don't care. If we increase the temperature, the kinetic energy increases, and we also see this broadening of the distribution. So here's the same gas at 273, at 1,000 and 2,000 Kelvin, and we see that the average velocity, or the most popular velocity, is higher, but we also see that the bell curve has spread out. It's not just moving over. Okay, calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So, root mean square velocity, that is URMS. And hopefully at least the root mean square would help you pick out this RMS thing from the list of equations. The root mean square velocity is the square root of 3 RT over M, molar mass. Molar mass in kilograms per mole. And here we're going to use a different value for the ideal gas constant, 8.314 joules per mole Kelvin. And M is in kilograms per mole. So we have the square root of 3 times this ideal gas constant times the temperature, 25 degrees Celsius is 298 Kelvin. So we got 298 Kelvin. And then xenon is what, 131.3. So we have 131.3 grams per mole. We have to convert this to kilograms. So I want kilograms on top and grams on the bottom, so the grams cancel out. We've got 1 kilogram. On the bottom, I write 1 times 10 to the 3, because that's what kilo stands for. And so this is 0.1313 kilograms per mole. Square root of that mess. So I'm going to deal with the numbers. Square root of 3 times 8.314 times 298 divided by 0.1313. 3 sig figs, so 238. And then the units. Ugh. Well, some of these you can see the kelvins cancel out, so that's nice, and the moles cancel out. But what we've got left in there is joules per kilogram. So we've got the square root of joules divided by kilogram. Joule is a unit of energy. I don't expect you to remember this, but I'm just showing you this so that you know there's a reason that it's in kilograms. So a joule is the same as a kilogram meter squared per second squared. So this is the same as kilogram times meter squared per second squared. That's the joule divided by kilogram, square root of the mess. The kilograms cancel out. Now I've got the square root of meters squared per second squared, and that is meters per second. So the unit up here is meters per second. And that's not something I'm going to try to trick you with. you could end up getting tricked using grams instead of kilograms. So this is because kilogram is the base unit of mass in the SI system. And so all the other units are based on it. So meters, seconds, kilograms. So there is the speed. Yes? That's an excellent question. How did I plug this into my calculator? So it depends on what kind of a calculator you have. So for the TI-36X Pro, over on the left side there's an X squared button, and above that is a blue square root symbol. So I do second and get that square root symbol, and then I do the stuff inside. 3 times 8.314 divided by 0.1313, and then when I press equals, it takes the square root of that and gives me, oh, I forgot the times 298. Yeah, you have to remember to do all the numbers. $238. Other calculators, you may need to do the inside, the 3 times 8.314 times 298 divided by 0.1313, and find that result and then take the square root of it. It just depends on what type of logic your calculator uses. Any other questions?
Answers for this type of question will always be in meters per second.
Yeah. So this part of the chapter is much higher level, more specialized stuff. And so with the more basic things, we screw around with you with the units, right? And we make you convert stuff because it's more basic. Here, I just want to know, can you use the equation? And typically in a question, you'll be given things with the correct units. A common exception, though, is that temperature. Temperatures are almost always given in degrees Celsius. I've never seen a thermometer that was said Kelvin because it's so easy to convert. You just convert when you need to. 238 meters per second. Here's a conceptual problem. Which sample of an ideal gas has the greatest pressure? Assume that the mass of each particle is proportional to its size and that all the gas samples are at the same temperature. And we can figure out just from looking at these boxes that they have the same volume as well. So the volumes are equal and the temperatures are equal. So what's different? The mass and the number, the amount of particles, right? So here we've got 1, 2, 3, 4, 5, 6, 7. This one's got 7 particles and 7 particles and more than 7 particles. I'm not going to count them. What does the pressure depend on? The mass or the number of particles? Depends on the number of particles. So which one's going to have the higher pressure? C. We don't have to do any math here, but we do have to understand the ideas. What about the relative pressures of A and B? Well, they'd be second, yeah, and they'd be the same as each other because they have the same number of particles. They both have 7. Any questions about that?